Boston area. I helped found the Boston Kubernetes meetup in 2015, 16, something like that. So that was pretty fun too, and it excites me to just get to expose to great content, you know. And getting great content is actually one of the hardest things of organizing a meetup. So because we want it to be good for you, like we want all the participants to come here and get out much better, much more capable, and to meet people that share problems and experiences, right? So with that said, I want to introduce our first speaker, is Ted Ross from Red Hat. Ted Ross is an open source software developer with Red Hat. He's a committer at the Apache Software Foundation, and he's author of the Apache Qubit Dispatch Router, now Skupper Router. He's currently devoting his time to the Skupper project. His background is embedded. Background not in my. All right. Background is in distributed systems. No, that's what I say. Embedded systems and networking. And one of that's primary interests is bringing the performance, scale, and reliability of networking together with the rich utility and developer friendliness of messaging into a compelling communication for offering for distributed systems. So with that said, Ted also worked at DAC, right? So like yes, former DAC. Thank you very much. So a round of applause for Ted. Thank you.
Did you make that up? Thanks everybody for being here tonight. So I've got 45 minutes, right? All right, I should set my watch. So I'm going to talk to you tonight about the Skupper project.
Please unmute this.
So I'm sorry.
This is muted, please.
That should be muted, right?
Yes, no. Okay.
So that's being picked up just by the microphone on the.
I will just mute it here.
All right.
Or you can take your volume down.
Holy
Just
cow.
make it to the last. Just make it very tiny, like very low.
Microphone level.
Or
Is that better?
yeah, that should be good, I think.
All right. Is it working now?
Yeah, it should be good.
Okay. So where were we? I'm going to talk about. Just keep going. I'm going to talk about the Skupper project. It's a project that's actually, the code base has been in development since actually before 2013. And more recently, the Skupper project itself is about 3 years old. So it is about cloud connectivity and solving difficult networking problems. And that's what we're going to talk about tonight. Should I switch to different? All right. Can you guys hear me if I don't use the microphone?
Yeah.
You get it here, right?
Yeah.
Yeah. So I don't need this. All right.
Yeah.
All right. Let me get started here. It's just a quick agenda outline of what I'm going to talk about today. So again, the theme is about digital networking problems with regard to digital transformation, moving to the cloud, going to more microservices as architecture. So I want to talk about in a little bit more detail about what those obstacles are. Anybody trying to do this will know what I'm talking
Maybe
about.
you can ask them to come over.
I'm going to draw a parallel to an earlier networking history. I'm going to try to make my point here a little bit, see how that goes. And I'm going to introduce a new abstraction for service interconnect, connecting components of distributed software systems together. That is what the Skupper project is all about. And at the end, I'm going to do a demonstration. So what is the problem? So the problem is that current networking infrastructure hampers efforts to modernize certain software systems. Does anybody agree with that? Or not? Let me just make some points here. So like firewalls, deauthorized zones, complex DMZs, like multi-layer DMZs, where you have internal and external, network translation, overlapping private subnetworks, particularly at the network edge. IPv4 versus IPv6. If you do business in Asia, you'll find there's a lot of networks out there that are only IPv6, and they interact with networks that are only IPv4. And all of this, slow pace of IT infrastructure changes. You've got this thing which is unreversed cumulative exceptions, so you get exceptions to make firewall holes, and you do a project, and then those holes never get closed back up again. So you get accumulation of security. And then also you go to distributed systems into the cloud, you're increasing your capacity rates. So when I'm talking about firewalls, DMZ, NAT, CIDR, IPv6, I'm not saying that any of these things are bad. In fact, they're all quite necessary. I'm not saying they should be subverted because they all have important roles, but I'm saying that they cause difficulties when it comes to moving on over the cloud. The other thing I'll mention is that it's a network we have is a network that does not provide global unicast or global multicast. I'm not saying we can't do this. We do this all the time, but the network doesn't do it for us. And we have to write software that works around the limitations of the network that we have. So the problem I'm talking about is really inherent to layer 3 networking as it exists today. So I'm going to try to illustrate this for the way it makes sense. So let's make reference to the open system interconnect model, the layers, 7-layer model. I've got 2 layers here that I really don't want to talk about, so I just labeled them as other stuff. But 4 decades ago, we were in lanes, and they used MAC addresses, and they were data links, and they worked well. We were limited in their reach in terms of distance, and there were ways of extending them and such, but basically at 2 lands, they did not talk to each other, and a host in one could not talk to the host in the other. But we solved that problem by elevating the abstraction. So we elevated the abstraction from the MAC address to the IP address. We introduced a new address as a way to reference things that we wanted to talk to. And what that did for us is it allowed us at layer 3 to think of this box as being able to directly talk to that box because it could use an IP address to talk to it. And at layer 2, of course, data link, where you've got a data link that has to find its own router. The router has to find other routers, has to find a path across the network that gets you closer to the destination. It has to find the router that's in the same network as the destination, and then it has to find the destination. This is all detail that happens at layer 2 that when you're standing at layer 3, you don't care about because it's all magic. At layer 3, I type in the IP address of a host in Tokyo, my packet will arrive in Tokyo. And I don't have to worry about the details. And if the details change, it still works. So this is great. This gave us this nice flat host network at layer 3. And that's actually what we have today, right? Not exactly, because what happened was the internet grew to the point where we used to run out of network addresses, network addresses. And in order to deal with the huge growth of the internet, we tried a couple of different things to solve the problem. The one that really worked was network translation. So we have net firewalls that will take an entire network that might have millions of addresses in it, but it's a private network. And now we have literally hundreds of billions of these private networks all across the world. Is that me? No, it's not me. That now we can connect to a single public internet. This works great, scales great, it performs great, it does everything really, really well. It provides connectivity, it even provides security. But what we lost was that flat network where anything can talk to anything. So this host over here cannot address this host directly. What it can do is, we've got applications like IRC or video conferencing or document sharing or email or whatever it might be that give you the illusion that you're talking directly to somebody else on the other edge. The application itself is actually written in order to give you that illusion. So what happened when we went from layer 2 to layer 3 is the network did the abstraction for you. But when we went from layer 3 to still layer 3, we have to actually build those abstractions into our applications themselves. And the reason this works really well, and the reason I believe that we haven't dealt with this yet, is because we predominantly in a client-server world. So most of the stuff we developed is client-server architecture. We would host a big server in the public internet, big monolith. We'd write clients, and those clients would interact with the server over a protocol we created using an address that we created, and it would work for that application. So we're not doing client server anymore when we're talking about microservice architectures and the kind of things that we want to do as we modernize software systems. We want to get away from microservices. We want to do client server, and we need to raise the abstraction for addressing it again like we did before. So this is what I'm talking about today. So if you have another picture of a network where I've now introduced a new type of address, which is I'm going to call it the service address. It sits at layer 7. You can call this the application address. You can call it lots of different things. I'll call it service address today. Now, I should mention that lots of people are doing things at layer 7, and lots of people make claims about layer 7. They say they're doing layer 7 routing, or doing DNS routing, or they're doing application-aware routing. That's all good. So it's always a case of looking into the application and doing something intelligent with the application in order to choose a layer 3 address for forwarding. So we're always falling back on layer 3 for our host forwarding. So we always have those restrictions and those limitations. So I'm going to introduce a new thing, which is a new abstraction we're calling virtual. Actually, my whole team is calling virtual application network today. So it provides addressing at service level, layer 7, like I mentioned. It's logically direct and independent of the line networks. The same bits we got when we went from layer 2 to layer 3, we go from layer 3 to layer 7. If I've got a network that spans, that's here in Plano, and if it's in Boston, and it's in San Francisco, and it's in Frankfurt, Germany, I've got things running all over. I want that to look like that network, that I can move things around it freely without having to worry about where they are or how they communicate. I want to raise the abstraction. So in this case, the addresses reference processes, an IP, the address references a host. There's a difference here. We're talking about specific APIs, or specific services, or specific sockets. That's what we're addressing here. I'm talking about primarily multi-access. So in a van, we assume that there will be multiple destinations using the same addresses. So instead of a unicast, I'm going to a single host. I've got an anycast where I'm going to a class of hosts where I'm going to load balance my traffic. I may want to have my service deployed locally and far away. So people in Dallas can have a service, people in San Francisco get San Francisco service. But if San Francisco's down, San Francisco clients can go to Dallas. I want to have, we want for purposes of high availability and latency, we have multiple instances of services. And we also want to event distribution over the wide area, something that the internet promises to do, but it doesn't accomplish in reality. So, like your MAC address, which are on-ramps, your NIC, the routers, your devices, but they're not really seen outside of your network. With a van, MAC addresses are then locally significant, and they're only used at one router to another. They're only used to connect things locally, and because they're local, then we don't concern ourselves about differences in IPv6 versus before, or having a network. I can have a client that's running on 10.1.1 IP address, and a server somewhere else that's running on 10.1.1 IP address, and they can interact with it directly. All right. I'm watching the time.
Is there any transmission?
I'm sorry?
Is there any transmission in between? Like, how does it work?
Hold that question. I hope I'll answer the course of things. If I don't, ask again, okay? So But I think I'll wait for your question. So what is this? Virtual application is the concept that I'm talking about. So the Skupper router is the implementation and realization of this concept. And so and I want to point out very important to say this is not an infrastructure component. This is not something that your IT department is going to slot into a rack and make it part of your infrastructure. It's developed. You don't need elevator just to use it. So you can also think of it as part of your application middleware or part of an application itself. And the idea is to build a network very quickly for the purpose of distributing your application where it needs to go. And then when you're done with it, or you can keep it up, or you can keep it or modify it as needs arise. So the routers talk to each other using a mutual TLS secret channel, router communication. The routers use a link state routing protocol to discover the topology and to compute the shortest path across the stuff so it figures out what the network is. So if you're familiar with DF from the networking world, SIS protocol, it's not that protocol, but it uses the same conceptual underpinnings. And the reason that was chosen is because that protocol, or that style of protocol, is very fast at responding to errors. So if you lose something, if the link goes down, if the region goes down, it adjusts very quickly. So you would typically build the network large with some redundancy to it, so that if something fails, then it got around that failure. So it automatically adjusts to failures and automatically adjusts to changes that you make. And this is a picture of what a network might look like. I've got, here's like a DMZ type of environment. Here's a bunch of edges that are connected in, and here's little mesh of edges down here that are connected in. So when this is all built, this from the application service standpoint, flat substrate, everything can talk to anything it wants to. All right. So what does this give us? It gives us the ability to consider the application shape to be orthogonal and independent of the network shape. And this is an important idea because we want to allocate services into the topology for business reasons, not for technical reasons. I don't want to have to put a server in a big server farm because that's where that's where servers go. I want to put a server where my customers are going to use that server, or I want to put my computes near where data is that it's going to be computing data on, or I want to put my computes in a place in the public cloud where it's least expensive at this hour, or where I have the availability of things like GPUs that I don't have available for the places. I want to keep my sensitive data inside my enterprise. I don't want to put it in the cloud. So those are the reasons why I want to put things in a network, not because the underlying network infrastructure requires it. The final bullet is kind of interesting one I won't go into in depth, but when you have a virtual application network running in production, you could actually take your laptop and say, I'm going to make that part of the network. And you can use that for development, debugging, testing. There's lots of interesting aspects of that. Some of the software that are in the distributed system and run them in a debugger or run them locally in a native environment. Okay. So what do we want to do in general with cloud native software development? We want to divide it into small distributed services architecture. We want to be able to migrate components incrementally. So if I'm going to take in on-prem, move it to the cloud, I don't want to have to break it in and put the whole thing over. I'd like to be able to do it piecemeal and a little bit at a time, test things out. You want to be able to grow your scale and reach as your business grows. You want to be able to locate, I mentioned this before, user-facing services geographically near your users. You want to scale your capacity up and down, match the capacity off the load. You want to deploy providers multiple availability zones for resilience. So availability is great. You can even use this to deploy on multiple providers as well. You want to keep sensitive databases inside your enterprise. I mentioned all of those things. A couple of use cases we are actually working on right now with customers and partners. One of them is machine learning, where this is a case where we have government laboratories where there's huge chunks of data in place and another big chunk of data, Los Alamos and one at Stanford Linear. They can't move that data around, but they want to be able to collaborate on machine learning. They need a way of easily connecting things together in two very private, very secure locations. They do it, I suppose, if they open up enough VPNs, it's actually prohibitively impractical. Migrating, like the old Kubernetes, and Red Hat, we have migrating to version 4. You want to do it incrementally. You don't want to have to just take the whole thing from one platform and then move to another platform. You want to be able to expand your cloud footprint incrementally. You want to be able to cluster for things like messaging. We actually call this faux stretch fake cluster, where you can one Kafka or Redis rather than queue in multiple clusters, as though you have a structure, but you're not actually doing the effort of doing that infrastructure work. You can have two completely separate Kubernetes that are using Kafka as a way to communicate as opposed to the underlying Kubernetes platform. Connecting multiple clouds, secure public access to on-prem database, mainframe. We've got a demonstration with IBM frame running data center, running DB2, and you have cloud-based workloads interact with that data in a secure way. All right. So I've used up half of my time. Is your question answered, or do you want to elaborate on your question?
I guess magic is the stuff, or like whatever the software that's running on. I guess that's going to become a bridge between the two.
Yeah, let me show you. So this is what I'm doing this demonstration. I've got it's an application a little bit better than a toy application because it's got some components, but I've got a database that is legacy. This database is already containerized. So I've got Postgres people. It's actually running on my laptop. And I've got a containerized workload written in Python, nearest prime. What it does is it interacts with this database using Postgres' libraries, standard protocols that are used. So nothing was modified here in terms of software. It does the normal thing. But when it interacts with the database, and it actually goes to the database, pulls out a number, a very large number of the nearest prime number that's back in. And also annotates each instance of itself, so you can see what happened. And then there's work schedule over the left here, which uses REST HTTP to schedule this work. So, and I can control that. So this is, when I talked about the applications, this is an application called components and how they interact. So let's go on the now, which is just a network. So here's a network I'm going to build, and it consists of sites, but I will add that site later on. I won't do it all at once. So I have here in this room, this is my laptop, a mini cube running here, and I've got those little ones running here. I'm going to set up, at least simulate a dual, not a redundant DMZ. So I've got two routers that are hooked up DMZ configured. And then I'm going to have, I've got OCP OpenShift running in IBM Cloud, Washington, D.C. I've got a AKS Kubernetes Azure running in Westera. And I will deploy routers in locations. So you see these arrows, how they all point into the DMZ. The arrows are the direction in which we've established connections. These are TCP connections running mutual TLS encryption. And the connections are inbounds, because that's where I'm putting my public addresses. Even down the line of AKS, I'm setting it up as handleless. There's no ingress on this cluster. Even though it's going to be able to provide service things outside of itself. Once we build this overlay network. So once these connections are established, the direction is no longer significant. That's the direction we go. We tend to go from more private to less private, more private to the public. Like outbound through firewalls, it's easier to do that way. And this is how you can avoid the use of VPNs. And again, once those lines are established, the arrows no longer significant, and service traffic flows bidirectionally and symmetrically. And then the third thing I'm going to do is this is the mapping of the 2 dimensions. So I'm going to I've got the database running here on-prem. I've got my schedule running on-prem, and I'm going to put these years prime workloads out in the public cloud, and they're going to interact. So what's going to happen then is this scheduler is going to use REST HTTP to control these nearest prime workloads, and the nearest prime workloads are going to take those instructions and interact with the database and do transactional reads and writes to the database. And clear? Let's see how it goes before I ask a question. So I've got a screen of each of these locations, and if I look at what I've got running here on my on-prem, I've got nothing running here. I'm in the default. See the Kubernetes service. Here in the TC running, and here in AKS, I've got nothing on my namespace. I've already set up namespace because I didn't know how much time I was going to have. And so what I'm going to do is I'm going to use this Skupper command line. This can be done a number of different ways. My demonstration by using command line because it's interactive, but this can also be done in more GitOps, based on YAML automated way like as well. But I'm going to say Skupper initialize, and I'll just give it a site name. I'll call it on-prem. And all this is going to do is drop the infrastructure into my namespace that I need. I'll do the same thing while it's running. It's already done. I'll do the same thing out here. Skupper net site name. CPDC. That one. Okay, so what happened when I did this? Now, is this text big enough for you to see? Is it too big for people to see? Okay. Is it good? All right, so it's wrapped around. So what is new now? There is the pod running routers. This is the data plane, and there's a service controller. This is the control plane for Skupper. And a number of sockets have been opened here, in the form of services, Skupper router. There's three of them get set up. And this is straight up Kubernetes stuff. So all I've done is deploy a router. And all I've done now here is the same thing. I've deployed a router location. Now, when I set PNDs, I ask them to create connection tokens. I can move these connection tokens around, and they can be used to set up these secure connections. So I'm going to say Skupper link create. I've got this token called token DNZ alpha. And I'll do the same thing with Bravo. So I've created these connections that go from the OCP into the DMZ. I can do the exact same thing from on-prem. Skupper create token alpha. So if I do status, and if I were to spell it correctly, it will tell me that I've got two links and that the connections were established successfully. Now, I will also then go to screen. I'll just ask for general status. And we'll go think for a minute. So this is going to tell me what's going on in my namespace. So in this default namespace, it says it's enabled. I call my site name on-prem. It's an interior mode that's not running the edge. It's not that important. The important thing I want to point out is it is connected to three other sites, one indirect. So that is what we expected. That's what we expected because we've got two DMZ sites and we've got the OCP one that's remote. And that's the one that we direct because there's not a direct to that. The way that you reach that site is going to be remote pod. So here's where the routing and forwarding and layer 7 comes in. it knows how to find path to that destination. So the network is set up, everything but the AKS that I'll do in a minute. So I want to show that being done later. So just to review, I've got service and pods here, the router, the regular stuff. And I'm going to, the first thing I'm going to ask Skupper to expose my database. So gateway is actually a way of saying I want to reach outside of Kubernetes. So I want to actually deploy a router. It's going to be on a hotline image. I'll get that started. And what I'm saying is that I want to use this address. I'm calling it DB. Just the database. And what I want to do is I want to expose my local host, port 5432. And 5432 is standard port for PostgreSQL. So it's saying I want to take my PostgreSQL to remote access. We want to make it available in this port. So let me go back to OCP DC. Remember I did this services and pods? And I'm going to do this. And repeat that command. Services and pods. And the only thing that's different now is there's a new service in here called DB. And this is the way it's glued up. So what Skupper and Kubernetes did was it said, well, I've got support on this edge system laptop, but in Washington, D.C., in the public cloud there that I have access to in namespaces, I have a service called DB. It's on a local IP network. Remember I said before, IP is locally significant, and it's available on port 5432, which makes it look like a PostgreSQL database. But there's no platform that has been used PostgreSQL. This service is a proxy for that database and can be used by local workloads to access that database. That's how it's going to work. So now if I apply the I'm setting on here prime workloads, containerized Gadban program, it's create and run. It is now running. So it has access to the database. It has actually authenticated the database and is running and waiting to be given instructions. But it is just a workload running in DC. There's nothing, it can't be reached anywhere. So if I come back to on-prem and I look at my service and pods, everything looks the same. I've got the DB all exposed here. But what I need to do is I need to ask Skupper to expose. So what am I exposing? Exposing the deployment nearest prime, and it's going to be running 48,000. So I'm asking Skupper to take that deployment that's running, crack its pod, and make it available on this overlay network, on the service network that overlays. Oh yeah, that just happened quickly. So I just reran the services and pods, and we see now a new service called nearest prime. So this is, and it's available on 48,000 on some local, locally significant private address I can get to this cluster. So same thing's now happening in the opposite direction. So I created a service that is now a proxy for that workload. Now if I go over here and see if I can do this. So I'm going to scale this up. So I'm going to scale it to. So now I've got two instances of this thing running. And I come back here and look at this again. You'll see that there is still only one nearest prime. So remember before I said that it's best to be multi-access. So the nearest prime is any kind of address, which means I want to look up my traffic to all the instances that are out there. And in this case, I'm interested in instances in my works, my news in DC. There's one last thing I need to do. This is the gateway forward. So I'm telling Skupper gateway, which means I want to reach in and out of Kubernetes, and I want to forward that service nearest prime out on port 8000. So what's happening now is there's a port open on my laptop at localhost. I'm port 8000 that is going to get me access to that workload running on OCP in DC. Clear? I see you not good. Let me fire up the load generator. Quarkus program. And this is the thing that's going to access that 48,000. It's going to access the nearest prime workload. It's going to do work in that database. Let's have a look at the database. I'll do a query on it. So I'm just a PC pull from the laptop. And I see that I've got a table of numbers that have not been processed. And I can come over and get my curl commands. I can curl my local. This is going to set the load on my load generator. So right now, I've got 0. And when I say load, I mean parallelism. So if I say I want to load 5, that's going to keep 5 requests in flight at all times. So let's just run for a second, and then I'll stop it and let it finish. So I just sent out 16 requests to go do this processing. So let's go to the database and see what our results are. See if it's different. So what's happening now is this load generator has gone out to DC and said, well, I want these nearest prime things to run and process do this lengthy processing on my database. And you can see that they're all done by DC, obviously, it's the only site I have set up. And this is the specs on the pod name, so that you can see that I've got, the pods are sharing the load. Some of them are doing more. It's not round robin because I think the reason that these 4 here were done by the same ones because these numbers are relatively smaller, so those work more quickly. So what this is doing is it's not round robin. It's actually keeping track of the backlog of each of the services, and it's attempting to equalize the latency. And that's how the balancing is being done here. So let's quickly go out and do this whole thing again. Actually, I think I've got these things in my buffer. If I do a knit, I'm going to set up my AKS one. And it will install Skupper router in my AKS interface. I said ingress down here because I don't want to even open up any ingress ports. Okay, I'm going to do link create on the 2 DMZs, complete the setup of the network. They should be on their way to being connected. One of them is, one of them is. That's good. It's on its way. And then I'm going to do the same thing I did before. Apply the nearest prime. I think I should have showed you here. Is that when I set this thing up and my namespace popped up with already populated with the things that it needed. So that those shared services that the database near prime came in, I joined this network. So I joined this network, the stuff I needed was already there. And now I can do the expose. Because this one hasn't been exposed. I only exposed the workload that was in DC, now I want to expose the European one that's on AKS. And again, this is another instance of the same service. So there's going to be no changes on the on-prem side. It's just got a single service that represents all of those workloads. And now I bring the workload back online. Let this thing rip for a bit and go have a look at my database again. You're going to see that AKS has joined the fray. So I've now, the ones that are actually being worked on. So those are in plan. Because remember I said load 5, so they're getting done. And now this work is now being shared and load balanced, not just across availability zones, but across continents and different providers and different vendors. All right. There's one last thing I want to show you before I've got 5 minutes and before I open it up for any questions. and this is kind of an important thing, and this resonates with some people, and some people don't care. I'm going to Skupper and already moved from the IKS. It was like he was never there. So this part of this part of the network went in, did a little work, and then exited. There's no firewalls left open. There's nothing I didn't have any phone calls. I didn't have any privileges to use this. I could just set this up as part of my application. And if I were to, I've got the loads going. So what we'll see at the end is going to be all these going at the end, because the AKS is going to be the one that's going to be done off the network. All right, my time is almost up. Are there questions?
Yeah, so I see that you queried like the database. So can you map any database particularly to it, or is there a specific database that you have to not create over again in order for it to work? So like for example, here now we use MS SQL.
Mm-hmm.
Could we connect like our MS SQL so that?
Yeah, the only thing that's really important. So the question was, I should Postgres SQL. Is there anything specific about Postgres that makes it possible? And yes, the only thing is that it uses a TCP port for remote access. So MySQL does the same thing, and IBM's DB2 does the same thing, and anything that runs JDBC does the same thing. So basically, any service that runs over a TCP port can be exposed and run over this. There's nothing protocol specific and needed. You got your hand first.
What about the security? Can anyone join the network without having any security? Or how does the security being there?
That's a great question about security. So the joining the network means like adding a router, like I've done. And I've got those tokens represent certificates that were signed by a certificate authority. So nobody that has a token, the only way you can join this network is if you have a certificate signed by the certificate authority that you signed for that network. So we intentionally make it very difficult to join the network. Once you're in the network, now you kind of have this distributed region of trust, if you will, where I said, my network's kind of spread around. Even though these locations now have access to the services I want, but joining the network is very difficult.
All right. I'm just trying to fill in some missing gaps in my understanding. So a couple of questions.
Yeah.
So how is it implemented? Is it as a Kubernetes operator? Skupper.
How is it implemented?
Mhm.
So the router?
No, the Skupper application.
The Skupper application is a Go program. It's not an operator per se.
Okay.
We actually have an operator for OpenShift that will install, but it works similarly to an operator that's looking at config maps and such. And it also, as an example, when I scaled that workload, that deployment from 1 to 2, then the operator, the control plane, or the service controller, as we call it, it's watching the API. It says, oh, I've got a new instance of this pod. I will create a new, I'll add it into the network, and I'll create a new connector for it out of the router. It's control planes that can go. It's very Kubernetes-like. The router is in C, and it's written kind of like a networking appliance.
Okay. Well, obviously, this is a networking service. So is it extending any of the CNIs? Do I need to have any CNI in place before I run it?
It's pretty agnostic to CNIs. It runs right down the middle of the road. It doesn't really do anything fancy. That's why I run on really old versions of Kubernetes and new versions of Kubernetes. It doesn't do anything really fancy with it.
Okay. And for the scenario you showed us, that's for a multi-cloud environment? Okay, so currently, if I don't have Skupper, what do I need to use? What will help me implement the same solution you just had, or maybe we don't we have any solution?
I'll go out and make the whole claim you can't do it.
It can't, okay.
But that's the whole thing. Like that, you could do most of it. The thing I think that you have a real hard time doing is the load balancing.
Right.
But you'd have to set up VPNs in and out, and you could probably be working with DNS tables and such to get things hooked up.
Okay. Well, I feel maybe this is something that the CNI writers or developers have to do, but I may be wrong. So do you have any plan of maybe giving it to any particular CNI or?
I don't know. I don't know if that's necessary. I haven't really heard that before.
Right.
So I consider CNI kind of a different layer that we utilize, right? We're using the services that are available to us.
Okay. Yeah. My way of saying it is that they should extend the CNI, but it's just my own understanding.
Got a question. So Skupper is nothing but an abstraction of the regular Kubernetes commands, right? But you abstracted with your own implementation. That's what they need to do. But that's fine. One question. Second question is behind the scenes, the same network policy is going to be generated, right? Or like we are doing differently to make the connection.
So there's two questions there. So the first one, it's not really a generation of Kubernetes. In fact, it pre-existed Kubernetes. When Kubernetes came along, we said this is a great place to fit into because Kubernetes makes it really easy to deal with, taking names, applying them to services and doing all that. It made it very easy to, solve a lot of those kind of the last mile questions. And Skupper works great outside of Kubernetes. As I should say that there's workloads, both client and server, that are under Kubernetes and work fine. Second question. Say it again.
So behind the scenes, the same network policies, whatever we used to do with, in Kubernetes, that's going to be happening behind the scenes, right? When we expose or do any
Yes.
Network addition.
Yes, the only thing you have to consider with regards to network policy is that the pod that is receiving your connection might not be the pod you think it is. Like in this case, you couldn't say I've got a network policy where I want a PostgreSQL pod to be able to take ingress from my end. You'd have to say I want my Skupper router to take those ingress. But we're actually working on having those policies be generated automatically by the control plane where necessary. In fact, at JP Morgan, where you've got things really nailed down, that kind of thing is necessary. All right, we're out of time. How do you want to handle this?
Yeah, I'll handle that. I will call in the next presentation.
All right.
Thank you very much.
I'm not going anywhere. I would love to discuss or answer questions that may come up.
Maybe 5 minutes break or?
Yeah, we can do I'm gonna try my for Lars. So a quick 5 break, so that gives time for Lars to set up. And yeah, thank you. Thank you.
Thank you.
Excuse me, you guys don't allow like people to use your guest network, right?
You have to create a. That's something urgent.
Yeah, I wanted you too. So.
That's right.
Thanks. Yeah, thank you. Have any more questions? Yeah, you can find me, and Theo knows where to find me. Sure, thank you.
Just
You
wanted,
got it.
yeah. What is your current biggest how many routers?
Most of the stuff we're doing great at, people are just starting to use it. So it's small stuff like that. But the router itself is designed for like more than 2 years. We've used it in other contexts. Well, it's scaled. We can go to thousands and tens of thousands.
Have you tried?
It's hard to get the server to run that on.
It's usually big.
Well, kind of alluded to it, but there's this interior, which is the arbitrarily shaped network. Right now, that's limited to 128 routers. 128. Architecturally, we could change that, but that's what it is. But the edges that hook into it are unlimited.
Yeah, and what is the cost of on top of TCP? So
it's unclear. It's not really constant. But yeah, there's some overhead, but it's worth to minimize it. It's. I mean, I want to say that for a running TCP stream, it's something like 20-ish bytes per segment. But for the setup, it's more for the setup. So we've run it.
Heartbeat. The TCP stream is like for heartbeat, like to see that they're like so the segue is like to is it monitoring like does it like logging internal like you have to look at
There's a whole thing.
yeah, but even within 45 minutes it was based off like end to end like
I know. Yeah, there's actually a GUI that we're developing in a way of monitoring what the connections are. So you can see that I've got this pod is made a TCP connection from this port through this path to that pod and sort of run that port. The idea being that you have server logs, you can correlate them to the traffic to find out what I got a malformed request, which pods are there.
do you change certificates very often, or they
There's for the underlying network.
yeah, like
Right now they're totally stable, but we're adding rotation. Yeah.
it's one good certificate or the boom.
Yeah.
what it's side to side then it do rotation. You can do one right like with the payload rotation and then disconnect it to point.
Yeah, typically you would deploy more than one
Yeah.
router at a location,
Yeah.
so you'd use Kubernetes to roll them out. So,
Yeah, thanks. Is it available to open source like the specs cover spec and like
Skupper.io is the website. All the code is if you're looking for specs, we'll work on
Using that is production.
Oh, I don't know.
They're trying to
That's good because you're in the real video.
Oh, demo.
I haven't. Good job.
Email me, I will send it to you. It'll come through. What's that? It's that's right. So many times. I actually trust it. It's failed on you guys. Yeah. It's not very happy. That's right. Yeah, this one's sure. So, I'm actually running this the intent was to so this the router was actually messaging. It was always a networks of brokers. It never worked. It's like people wrote them. So what we did is we separated.
All right.
Let's make a router that gets things quickly to where they need to go. That's
All right. Awesome. Thanks, everybody. So we're gonna go to our next presenter. Our next presenter is Lawrence. Lawrence is a software architect at Sol.io, currently focusing on vSphere, Cilium, eBPF, and how these technologies can be used to keep together to provide a powerful application networking platform. Previously, he spent time as a field engineer and worked directly with organizations of all sizes to architect, adopt, and implement various application networking components, including service mesh and API gateways. I was also going to make a plug for all the jobs that we have here, but HR just left the room. JP Morgan has more than 1,000 open technology positions in this area. So just Google JP Morgan careers. And if we can refer you, we also make money. So there's that.
Did you see it?
Yeah, so it's telling me to do mic and cam. So mic, do we need mic from here? Okay, so we should exit this slide.
Yeah.
I haven't seen you though.
Whatever. Okay. I might have to.
Now, once you share your screen,
Yeah.
okay.
Okay. Yeah, it's muted. Yeah. Okay, and then I need to share my screen to Zoom, right?
It should be sharing already. Or did you stop?
I think I stopped it, yeah. Okay.
Yeah, we should be good.
Good? Okay. All right. Okay, can everyone hear me? Okay. All right, so my name is Lawrence Gadban. I'm going to be talking about Cilium and eBPF. I work for Solo.io. I'm a software engineer here on the thing. It's software architect. Doesn't really matter. I work on the software there. And so today we're going to be talking about Cilium and eBPF. Why are we here? Why am I here as Solo representing for Cilium? So at Solo, we have a platform we call the Glue platform, which is an application networking platform that has a gateway offering, a mesh offering, and now a network offering. And as part of our network offering, we use Cilium. We integrate with other CNIs, but we think Cilium is kind of the future of the CNI space in Kubernetes. And so we've kind of been working on that for a while now, and we're really excited about it. So we'll start off with what is Cilium. So on the left, there's a diagram that we'll kind of look more in detail on. On the right is something just straight from their documentation page, where it describes it as Cilium is an open source software for transparently securing the network connectivity between application services deployed using Linux container management platforms like Docker and Kubernetes. Essentially, it's a container networking solution, and it runs on Kubernetes, it runs off of Kubernetes, but the primary use case we see is in Kubernetes as a CNI plugin. And the reason why Cilium is becoming very important in the cloud native landscape is because it's built on top of eBPF, which is a Linux technology that essentially allows you to dynamically instrument the kernel with programs essentially. And so they also call out here where eBPF basically allows you to deploy security policies and do network configuration without any changes to the application code or the container configuration. And this is really powerful. So we'll talk a little bit about why eBPF and what is eBPF, because it's important to understand why Cilium is becoming so popular and why Cilium is so powerful. So eBPF, as I mentioned, is a technology that allows you to load and run custom programs, sandbox them. So you can run these programs without having to modify the kernel. The reason it's called eBPF, it is based off classic BPF, which is how things like TCP dump worked, and the eBPF used to stand for Enhanced or Extended BPF, or it's Extended Berkeley Packet Filter. That acronym is kind of not really an acronym anymore because eBPF can be used for much more than packet filtering. And so you write these programs, you deploy them into the kernel, and now you can modify the kernel functionality on the fly. You can do it dynamically, and what that means is that you can essentially change the kernel without having to put in a patch and wait a year or more for it to get rolled out to somewhere. It's event-based, which means that these programs that you write, you have different hook points that you can attach them to. And once you have attached it, as the events fire at these various hook points, your program runs and can do whatever it is that you've programmed it to do. So an example that I've called out here is a K-probe. And so K-probes have existed before BPF, but essentially what you can do is attach it to any kernel function. You can attach a piece of functionality. And that means that you can, for example, say you want to write a K-probe that will happen on TCP Connect. So whenever an application makes a system call into the kernel to connect to a host, you can have a program that runs, and that program will be able to inspect and potentially modify some of the parameters of that system call. That has already existed with something called Linux kernel modules. The reason that eBPF is, or one of the reasons why eBPF is much more powerful than that, is that there's a guarantee of safety with eBPF programs. And that means that this verifier is going to inspect the code that you've written. It's going to make sure that it doesn't loop endlessly. It doesn't modify data that it shouldn't be modifying. And once only after the verifier has said that this is okay to run, will you be able to load it and attach it in the kernel. And so with all of that combined, eBPF has really kind of opened up the door for basically, adding all sorts of kernel functionality. And we'll actually look at some of the main use cases right now. So networking is the big one. Well, actually, they're all big, but networking is kind of the canonical use case. Especially as I mentioned, classic BPF was used for packet filtering. That's how TCP dump worked. Because if you think about it, you want to capture packets, but you have an expression that expresses what packets you want to capture. You don't want to capture every single packet flowing through the system. And so what eBPF did is you're basically writing this code that gets translated into essentially, it's kind of like a virtual machine that will run this code in the kernel, because when you're filtering packets, you cannot have every single packet be copied out of the kernel to user space and then have your user space application, inspect it and say, okay, I don't care about this port, so now I'm going to drop it. So you need a way to do that in the kernel, and you need a way to do that efficiently. So that was the original use case. But now with eBPF, you can do much more than packet filtering. So basically, you can think about every hook point in the kernel networking stack. You can inject the eBPF program to interact with. And so essentially, you have programmatic access to processing the packets as they flow through the system. And you can kind of think about it as you're programming your own network stack. It's a pretty significantly powerful tool. Security is another one of the big use cases. Again, you're running inside of the kernel, so you can do things that, you can write policies that will stop something from happening before, it can actually do damage. You get to see the data at the kernel level, which basically gives you unparalleled visibility. If you think about security in terms of network security, since I just mentioned, you have hook points in the entire kernel stack, eBPF can be used as a great fit for network security. And that's one of the things that Cilium does really well. The last kind of big touch point is observability. So again, as data, or as stuff is happening in the kernel, you have your programs running in the kernel and you can observe what's happening. So I mentioned earlier K-probes. Trace points is another good example where a trace point is essentially a site in a function in the kernel that the kernel developer has said, I want to be able to trace what's happening here. And with eBPF, what we do is write a program that says, I'm going to touch this specific trace point, and I get access to all of the data that this trace point gives you access to. So kind of going back to the TCP Connect example, if there is a trace point in TCP Connect, and let's say that you get the source and destination IP, source and destination port, you can write a program that hooks into that trace point, and you'll get that data and you can do something with it. So in case of observability, you can log that. So think about getting TCP dump, but think, getting it essentially for free without having to run a TCP dump. And so I also call out that because of the fact that you're running in the kernel, you can process events in the kernel without having to copy them to user space, kind of like the TCP dump example. But you can do that for anything, it's not specifically tied to the network stack. It's not tied to processing TCP. You can do that for syscalls. One of the cool examples with observability is you can basically hook and watch every single open call. So anytime a file is open, you can know the PID, you can know the user, you can know the file path, and so on. You can do all of this in the kernel, so you can do it for essentially every single one of them. So let's dig a little bit more into the networking use case. That's kind of the fundamental thing that Cilium does. Everything else builds on top of that. So Cilium is primarily a CNI plugin. We were talking about CNIs earlier. The basic hacks of the CNI is to set up the networking interfaces for pods as they spin up in your Kubernetes cluster. So you have a pod that spins up. That pod needs to be able to talk to other pods in the cluster. It needs to be able to call services. It may need to talk to services on the host that are not in Kubernetes, and so on. So the CNI that is running on that cluster needs to set up those interfaces so that network connectivity is established. You also need to be able to route between nodes. So you have a Kubernetes cluster with a bunch of nodes on it. Regardless of where the pods are running, everything needs to talk to, every pod needs to be able to talk to every other pod, unless there's a network policy blocking that. But from a network connectivity standpoint, those pods should be addressable by the other pods, regardless of the nodes they run on. And so one of the other jobs of the CNI is typically to set up routing and so on, so that the nodes can talk to each other as well. So Cilium provides all of that as part of its basic CNI tasks. But there's a lot of other things that it can do because of the fact that it's built on eBPF. So one example is kube proxy replacement. And we'll get into more detail on all of these right now, but kube proxy at a high level is what's responsible for service load balancing, essentially. So when you have a pod that talks to another service, that service is backed by several other pods. And the kube proxy component provides a way for you for that load balancing to occur. And we'll go into more details, so I'm not going to talk more about it right now. One of the other things that Cilium can provide is transparent encryption through either IPsec or WireGuard. And what that means is with the node-to-node use case where you have a pod on one node and a pod on another node, without the presence of service mesh or something like that, that traffic is going to be plain text unless the application set up some sort of transport security themselves. And so with transparent encryption through Cilium, the node-to-node traffic is automatically encrypted with either IPsec or WireGuard, applications don't have to care about, essentially. And that means that all node-to-node traffic is encrypted. And then network acceleration is another interesting one where for connections that are happening on the same node, so you have two sockets talking to each other, and really they're different pods, but it's really just sockets on the same host talking to each other. With Cilium and eBPF in general, not just Cilium, you can essentially use something called a sock map, which will keep track of those sockets. And as events occur, such as opening the connection, establishing a connection, and then sending and receiving messages, the sock map will hold the sockets in that connection, and you can essentially write data from one socket to the other without having to go through the entire network stack. So let's dig a little bit more into it. This diagram kind of shows at a very high level. I don't know how easy it is to see. But basically, so you have the Cilium control plane at the top, and the ways that you can interact with it. So there's a CLI. It can be driven through, GitOps style with YAMLs and so on. Each node gets a daemon, or an agent is really what it's called, the Cilium agent. And that is what essentially sets up and runs the VPF programs that are necessary on the node. And then it will inject in various places in the kernel the VPF programs that kind of make up the data path of Cilium. And so at the bottom, there's a few containers, and then there's a F0, NIC, or physical network interface. And what this is trying to show is that for all communication from the physical devices and the various containers on the kernel on that node, there is a VPF program or several VPF programs that essentially are doing all of this stuff, right? They're enforcing policies, or they're doing smart network translation and so on. And those VPF programs are running on the node, and they're attached to each container. And so the container networking is provided by this data path that's built up of standard Linux networking, but primarily eBPF. And so just a quick refresher on Kubernetes networking in general. So because we'll use this to build up and how Cilium actually works. So you have a node. I don't know if that's big enough, but I'll talk through it. So you have a node, and on that node is the kubelet, and the kubelet is kind of in charge of running stuff for that node. The pods that get scheduled to this node, the kubelet's job is to make sure that all of that is running on. So you have a container runtime. In this case, it's container D. I probably should use Cryo because of all the Red Hat folks, but container D works also. Then you have the CNI plugin, which does all of the CNI tests that we were just talking about. So the example is a pod is scheduled to run on this node. And so what do we have to do? The kubelet has to delegate the tasks necessary for spinning up this pod, and in order for it to run. So the container runtime is responsible for actually setting up the Linux namespaces, running the containers and so on that make up that pod. And then the CNI is called, and the CNI's job is to, in this case, let's set up the interfaces for that pod. So one example here is using a VEF pair, where one side of the pair will go in the pod, more specifically in the network namespace for that pod. The pod sees it as F0 interface. And then there's the other side is living in the host network namespace of this node. And so what that means is, as the CNI sets this up for every pod on the node, now those VEF pairs are, for each pod setup, that the routing exists. So now you have networking between pods that are on the same node. And then in the case where you have to leave the node, the routing is set up, or the rules are set up to where the traffic will actually leave through the correct interface and go wherever it needs to go. So why do we care about that? The standard Kubernetes networking. So with the way that this is typically implemented, or I guess was typically implemented, there's various points in the kernel, in the NetFilter subsystem of the kernel, for how you do routing rules, or just basically moving packets around. If you ever used IP tables and set up a firewall with that, you're familiar with the various points. One of the interesting things, though, is there is ingress and egress hooks at the beginning and end of this. The TC ingress and the TC egress hooks. TC stands for traffic control. Those happen before and after all of this other stuff in the NetFilter subsystem, basically. And so what's interesting about that is you can attach you can attach eBPF programs to the ingress and egress. And so when you're utilizing the CNI, since the CNI is setting up those interfaces, you have a port point that you can directly interact with that interface. So, for example, you can attach an eBPF program to it as you set it up. You also get a life cycle because the CNI is called every time that a pod spins up, right? It says, okay, I need to add an interface for this pod. So the CNI will look that up. You know that the pod is spun up because the CNI is being called, and you get the opportunity to attach those programs to it. So now you can build up your data plane with the interfaces and the eBPF programs that are attached to those interfaces. So what you end up with, at least in Cilium, is something that looks like this, where you have, in this example, you have a Kubernetes cluster, you have 2 nodes, and you have various pods spin up on the different nodes. There is the standard kind of Beth model where you have an interface in each pod that each container will use for traffic, and then you have another pair that lives on the host namespace. That's owned by Cilium, and now you have this Cilium data path where the eBPF programs that make up the Cilium data path are attached to each one of those interfaces, and also the physical interfaces that actually provide the cross-node communication. So for the cross-node communication, there are a couple of options. There are 2 called out here where you can use encapsulation. For example, VXLAN, it's pretty straightforward, right? You have this overlay network that Cilium has built up. You need to talk between nodes, so you can use VXLAN for that. That's actually kind of the default mechanism because there's not a whole lot of dependencies on it. If you have a flat network, and based on the last talk, I don't know, it kind of depends on what you mean by a flat network. From this perspective, if you have addressability at the L3 layer for all pods in the cluster, you can use direct routing. In fact, this is how some of the clouds do it. So like, it's actually interesting because now Cilium is used for GKE's data plane version 2. You can run it on AWS, and Azure at KubeCon just announced that they are going to support native Cilium as well. So the direct routing model makes sense, especially if you're getting a managed, if you have a managed cloud, because it's usually built into the cluster directly. Okay, so now we'll talk about kube proxy replacement. Typically, kind of the standard way right now is to use an IP tables-based kube proxy. In the early days of Kubernetes, I'm pretty sure there was actual user space proxy that handled every service call and actually forwarded to the right location. The common one right now is IP tables. So if you look on a node in the Kubernetes host network namespace on one of your Kubernetes clusters, there's probably a bunch of IP tables roles that say when traffic has been sent to the service bit, right, the service virtual IP. What I'm really going to do is use IP tables to do some probability-based routing where I will go to the various endpoints that make up the Kubernetes service. You know, it works, and it has worked for a while. The challenge is that if you have a very large cluster and you have a lot of services, as the IP tables list grows, it's essentially an overhead operation to either search through it or delete it because of the way that it's implemented. And so I actually used to run OpenShift clusters, and we had basically fit as much stuff as you can onto a cluster. So we were looking at 5,000, 6,000 to 10,000 services. And when you do that, it's noticeable how much time it's taking for IP tables to be able to keep up with that. So with eBPF, because of the fact that you can run essentially programs in the network stack that you write, what Cilium does is it allows you to run a program to keep track of the various services and actually use a hash table to look up and to insert and to delete for all of the operations that make up the services in your cluster. And so you get this O of 1 runtime for the kube proxy functionality. And so it's a pretty significant benefit. This is actually Cilium benchmarking, so take it with a grain of salt. But it does hold up that as the number of services, the number of Kubernetes services grow, if you use a hash-based implementation, you get some pretty nice benefits. And maybe it's not the biggest thing, but as you start trying to shave off seconds because of the fact that you have 10,000, 20,000 services in a cluster, this is something that can help. Okay, so transparent encryption. This diagram is not the best one. It's the best one I could find. I didn't have time to make one. Essentially, what this is showing is that here on the left, we have a client pod, and on the right, we have an Nginx pod. So client server, we're trying to call the Nginx pod, and we're going through the Cilium kind of standard. We go through the S0 interface. We come out the other side of the VET pair without doing anything to either the client pod or the Nginx pod. When you have transparent encryption enabled, what will happen is the data flow will go through this. In this case, it's using WireGuard. It will go through the WireGuard interface, and then WireGuard is set up. So basically, the agent that runs on every node will know about every other node in the cluster, and you'll essentially negotiate. You know of each other node's public key, and so you can set up a WireGuard encrypted connection from each node to each node in the cluster. And in this case, for when the one on the left talks to the one on the right, it will transparently go through the WireGuard interface, get encrypted, go out the S0 using that encrypted connection has already been established. It will come in through the WireGuard interface on the node that it's going to, and then the Nginx pod has no idea that happened. But as data has transited from one node to another, it was encrypted. So this is really nice. Typically, you need to use something like a service mesh or Skupper to do something like this. So the fact that you kind of get this for free when you use Cilium is pretty cool. That being said, this is not mutual TLS, so you don't have that kind of. Actually, I'm going to save that for later. You don't have a cryptographic identity for the services talking to each other, and we'll get into that in a second. But essentially, this is a nice feature for you don't want to have plain text, leaving from node to node. So the network acceleration use case, this is one that is actually easier to illustrate with something like a service mesh. So in this case, this is an Istio-based example where if you are not familiar with Istio is a sidecar-based service mesh. So there's a sidecar proxy that's injected to every pod, and that is what the proxy is what does kind of all of the higher level layer 7 features, as well as load balancing and also mutual TLS and so on. But in order for that to happen, that means that each container all of the traffic gets redirected from the container to the sidecar proxy, and then traverses the network, wherever that is, to the other container, to the server, and then that traffic goes to the sidecar proxy, and then back through the network to get to the actual the network stack to get to the actual container. So with acceleration, what you can do is essentially cut out all of the network stack in the kernel, because as you watch connections and as you understand what connections are happening on the node, you can keep track of the sockets that make up that connection. And essentially, as in this case, the service here sends a message, it goes through this socket. You have a hook point and you keep a map of these sockets. So you know that in the case of this flow, you really just write the data to this socket rather than having to go through all of the layers of the network stack. And so this is actually something that is not, again, this is eBPF, not Cilium. In this case, it is Cilium, but for example, in the Istio service mesh use case, there is a community project called Marebridge that does exactly this. At Solo, we have something that does this in our Blue Mesh product. Essentially, this is something that you can do using eBPF, and you can do this for pretty much as long as you can track the connections, you can get this benefit. This also comes with a performance improvement. It's not astronomical, can't say that word. It's not huge, but it is good enough to shave off a few milliseconds here or there. And if you have a microservice architecture with a long call graph, as you start shaving off seconds of the tail latency, it does add up. Okay, so security. Security in Cilium, kind of the fundamental concept are endpoints and identities. The easy way to think of an endpoint is a pod, and the identity is essentially an identity built up of the labels on a pod. So if you have two pods that are created by the same deployment, because of the fact that they have the same labels, that's going to result in the same identity being used for each one of those pods, even though they're distinct pods. It's worth calling out that it's important to know that that's not a cryptographic identity. It's something that's based off of the control plane, watching for IP addresses and matching that to the labels and so on. It's something that can be tricked. I have a blog here where we kind of explored why that identity is not necessarily foolproof. So if you're interested, you should check that out. But with the endpoints and identities set up, what you end up with is the ability to do network policies. And so that's not crazy that most CNIs implement that, where you can write a Kubernetes resource that will control access between pods and so on. So for example, with you writing a layer 3 policy, if you have, for example, we have 2 pods on the left, foo and bar. One has a role of front end, one has a role of back end, and then you have a pet store application, which is kind of your API. In this case, we wrote a network policy that says, I'm only going to allow ingress to the pet store from a front end application. And this is actually wrong, we should say role, not access. But anyway, it doesn't matter. I only want to talk to pet store. And so with the network policy in place, the front end is allowed, back end is not allowed. Okay, so then you can go a little farther and go to layer 4. So you can include ports, for example, right? So in this case, I want the front end to be able to talk to pet store only on port 8080. So that will work, but back end, or if front end tries to talk to some other port, like for example, some admin port, that connection will be dropped. Cilium goes a step farther. They use, so you can, if you can see here, there's a Cilium network policy instead of the network policy that Kubernetes standard API. Cilium network policy adds some other features, for example, layer 7. So you can do a network policy that on top of what we just looked at for the label, the port, you can also now say that I want to only allow a get to the /pets endpoint. So if the front end app makes a request to the port 8080 and it's an HTTP get /pets, that's allowed. But if the backend app tries to do that, it will be allowed, will be denied. If the front end app tries to make a request to, in this case, a post instead of a get to, this out of the way. The post instead of a get to /pets, that will be denied. The way that Cilium implements layer 7, though, is where it's important to know that that is not fully implemented in eBPF because it's very, very difficult to have a full HTTP parser and processor written in eBPF. So the way that it's solved is using Envoy. So there's an Envoy proxy running in the agent, essentially, and that the BPF data plane will redirect traffic to Envoy in order to implement layer 7 policies. And then, depending on the result of that, it will then continue in the BPF data plane. Okay, so almost out of time. Observability. Hubble is a subsystem of Cilium that kind of provides its observability. Basically, because of the fact that the data plane is processing all of, basically every packet that flows through Cilium using a CNI, you can see it, right? Like based on the examples that I was talking about earlier. So Hubble gives you a lot of visibility essentially for free. And the way that it does that is by having the eBPF programs that are attached to the interfaces as the traffic flows through it. They essentially will take the relevant data that they need, generate an event, and emit that to an eBPF map that lives in the kernel, and then they kind of like process that asynchronously. And so there's nothing that's happening on the hot path as far as observability goes, but you still get this really rich observability data. So you have a Hubble agent essentially that's really part of the Cilium agent, but that's what's running on each node, and that's what's looking for those various events that happen. And then there is more of a control plane that kind of can extract all of that. And you can, for example, get metrics in standard Prometheus style. There's also a UI web application, and you can also use the CLI to kind of inspect that. What you really get is basically standard network visibility. that you would, that's really important. So you get a bunch of flow visibility. In this case, you can see forwards and drops, and so on. You can't really see it, but you can see like the reason for drops, for example, if it's an L3, policy denying it, or so on. And you get all of this without anything happening in the applications, right? It's all done in the CNI layer, and it's all done with eBPF. The other cool thing is that you can build service graphs off of this because of the fact that you can track flows. You can build essentially a graph of similar to what you would get with distributed tracing. You can track connections and build a graph of your service dependencies without having to integrate applications, which is a really cool feature. So I didn't think we're going to have time for hands-on. So I wanted to do a quick shout out. We have Solo Academy, which you can sign up to take workshops, essentially hands-on workshops. You don't have to install anything, it's free, you just have to register. We have a Cilium class that kind of goes through all of this, and you can do it hands-on. We use a tool called Instruct, which is actually really cool. It's similar to Catacoda, if any of you have used that. But if you want to get hands-on with some of this stuff, I highly recommend checking this out because it's a very easy way to be able to run through some of this. And that is all I have. I think we have time for questions. Yeah, okay. Any questions?
Do we have access to the slides?
We should. Yeah, I can. Yeah, I'll work. Yeah.
Okay, then one more question. Personally, I've used Calico and WeaveNet,
Okay.
but I haven't used much of Cilium. So if you were talking to someone using Calico, what would you say is the number one thing to switch to Cilium?
So it's a good question. I mean, one of the biggest reasons, so at Solo, we've talked to a lot of people that are interested in Cilium, but they don't want to take on the extreme amount of work it is to switch CNIs. And so I want to preface the answer with that. Like, I don't think you should have to switch, right? Like Calico is really good CNI. They've actually started using eBPF as well.
Right.
The biggest reason though, so one is the community. Cilium is kind of exploding in popularity, and not that popularity makes it good, but like I mentioned, most of the cloud providers are using it as their actual networking implementation. So there's a lot of eyes on adding features, fixing bugs and so on. The other thing is that since it's all eBPF, way more eBPF native than Calico, there's a lot more that you can do with it as far as like the more advanced use cases. So like one of the things that they actually just announced at KubeCon, last month, they are pushing new features into the Linux kernel where now you can use, basically they're adding helpers that allow you to do things where the VEF networking for all of basically, kind of the standard way of doing networking, right? They are adding a way of essentially giving you near native performance where there's no performance impact of having those VEF pairs. And so like things like that, where it's like the Cilium, Cilium has a lot of the kernel engineers that are eBPF co-maintainers and so on. And so what that allows you to do is like, they're kind of pushing the kernel forward that's going to enable all of this good stuff. It's probably not a good answer, but there's a lot of really good stuff coming, I guess is what I would say.
Okay.
Other than that, like I said, if you're running like a production cluster, I would not say, go and switch to Cilium because it's not, unless you need some of the features that we talked about that you cannot get with another CNI.
Okay.
Thank
you. Thanks.
Yep.
So does Istio and Cilium work together as a single set? How does it?
Okay, so the question is, does Istio and Cilium work together? It's a really good question. It's kind of a complicated answer, unfortunately. So at the highest level, it should be fine, right? Like Istio is primarily operating at a higher level, and all that really is important is redirection from the application container to the sidecar. There's a new mode coming called ambient. I don't know if you've heard of that, but that's going to remove the sidecar. But even still, the important part of the networking layer is that I need to get packets that are leaving or coming to an application in the mesh to the sidecar or whatever the proxy is that's handling it, right? For the most part, it does work well. But because of how Cilium implements some of this stuff, it doesn't always play nicely. So like there are some features that you cannot have turned on in Cilium to work with Istio. Cilium actually has its own distribution of Istio that to work with, all the features and so on, because they basically, there's data plane stuff built in to handle that redirection. The problem with that is that is kind of outdated. I think it's on like Istio 110 or something like that, and Istio 116 is just coming out. So it's kind of falling behind the community support, essentially. There's also something complicating, which is that Cilium is trying to do its own service mesh, which has a completely different model. And that is essentially why the Istio integration is in this type, because they're kind of moving in their own path with Cilium service mesh. We actually at Solar are kind of interested in doing both. And so we're kind of working on how we can have Istio and Cilium play nicely together for all modes and keep up with kind of the Istio versions. So to kind of take a step back, I would say they should work well together. Depending on what you're trying to do with Cilium, it should work fine, but it won't be great in all cases. I don't know if that answers the question.
One more question? All right. Cool. Thank you very much.
All right, thank you.
All right, folks, so that was it. Thank you very much. We still have this. I think if you want to take your whole box home, please do it, because we have no interest in